Hi, in this video we'll be talking about another prime factorization technique. So let's say you need to find prime factorization for all the numbers from 1 to 10 to the power 6. Okay, so before we talk more about the problem, let's quickly revise what prime factorization is. So this would be the prime factorization for 60 would be 2 into 2 into 3 into 5, right? Yeah. So it's basically decomposing it into primes. Okay. So let's say we want to find out prime factorization for all the numbers from 1 to 10 to the power 6, or let's say we want to find, like, there would be q queries. Okay, there are q queries, and in each query you will get a x in the range 1 to 10 to the power 6. Okay, you need to print the prime factorization of that particular number. Okay, so if x is 60, you print 2 comma 2 comma 3 comma 5 and so on, right? So let's suppose there are q such queries, and let's say q can be up to 10 to the power 6 as well, and for each query you will be given an x, and you need to print the prime factorization of that x. Okay, now how do we solve for such large constraint? Now the direct technique we have for prime factorization takes us order root n, right? For any x given to us, it will take us order root x, and that gives us a prime factorization. We have already discussed this particular algorithm previously, but that won't satisfy for our need, because root x in this case is up to 10 to the power 3, and there are 10 to the power 6 queries, and that would lead to 10 to the power 9, which won't pass in a second. Okay, so we want to do it better than order root x. Now first of all, we need to understand, can we even do this better than root x? Because remember, we discussed about divisors, like there are 2 into root n number of divisors at max, right? So what about prime factorization terms? So to solve this particular problem, we will use the idea of precomputation, that for each of the numbers we will try to store something that will help us to factorize the numbers very easily. Okay, so we will try to store something that will help us to solve it very fast. So this is the whole idea of precomputation. So before we go into like what we store and all, we need to understand how many prime factors can a number have. Okay, so let's suppose this 60 has 2, 2, 3, 5, right? There are 4 prime factors. Okay, how many prime factors can a number have up to 10 to the power 6? Or let's say for any given n, what's the bound on the number of factors? So if you think about this particular bounding, it is pretty less. Why? Let's say for this n, the smallest prime it can take is 2, 2, 2 and so on. Let's suppose a lot of 2's make this n. So number of prime factors, number of 2's over here would be 2 to the power count, and c will be equal to log 2 of n, right? So even if all the factors are 2, like the count is maximum and all the factors are 2, the maximum number of factors that you can get is around log n. Okay, so the number of prime factors for any number n is bounded by order log n. Make sense? Because every time you multiply a factor, the number at least gets doubled, right? Because every prime factor is greater than or equal to 2. So the number of prime factors can be order log n for any number. Okay, so now if we know this, how do we find out these log n terms very fast? Okay, so there will be very few terms, but how do we find them very fast? Because we would have to answer, even if we could answer each of the queries in order log n, then only it's working, or else it will not. Okay, so we will try to store something. Let's look into what we will store. So for every number, we will try to find out the smallest prime factor of that number. Okay, now what is the smallest prime factor we are talking about? So let's say 2 smallest prime factor would be 2, 3 smallest prime factor would be 3, 4 smallest prime factor would be 2, because that's the smallest prime that which divides 4, right? 5 smallest prime factor would be 5, 6 smallest prime would be 2, 7 7, 8 2, 9 3, 10 2, 11 11, right? I hope you got the point how we are calculating this. So if you write the factorization, which is the smallest prime which appears for this particular number, that we are writing in this particular array. Okay, so we will try to create this SP array for our help. Now why are we even creating this particular array? So let's suppose now you need to, let's take an example of 8. You need to factorize 8. So for 8 you look up that, okay, the smallest prime factor is 2, so it's 2 multiplied by something. Now what is this something? that will be the prime factorization of 8 by 2, which is nothing but 4. So now we try to find out the prime factorization for 4. For 4, we know that its smallest prime factor is 2. So we write 2 and then we jump to 4 by 2, that is 2. And for 2 we know it's 2, so we write 2 and then we terminate, because we have already reached 1 and there is no prime factor, right? So what we are doing is, for every number we are just finding out the smallest prime, we are just removing that smallest prime from the number, and for the smaller number that we get, we are again using this SP array for that smaller number to calculate the prime factorization, right? Okay, so basically the kind of recursion that we are using is like prime factorization of some number x would be equal to smallest prime of x multiplied by prime factorization of x by sp of x, right? Is this clear? So this is the whole idea that we are trying to use in this particular logic, and we know that this would terminate in log n number of terms, because there are at most log n number of prime factors for a number, right? So first of all, we need to create this SP array. So we will use the idea of sieve to calculate the SP array. Now first of all, we initialize all the SP of I to be I, okay, and then once we have all the SP of I to be I, so initially like 2 is 2, 3 is 3 and 4 is 4 and so on. So let's just talk about 2, 3, 4, 5, 6, okay. So these are initially 2, 3, 4, 5, 6, okay. This is the initial values. Now we loop from start, and if it is I, if SP of I is I, that means it's a prime. Now why this means prime? Because nothing else reduced it. So we are using an idea similar to sieve. So in that we kept is prime equal to 0 or 1, right? So we will over here use SP of I, and if it is not yet touched, that means it's like it's untouched and it's a prime. So we use this particular number to like calculate the SP of next numbers. So for all its multiple that we look into, okay, so we go into the multiples of 2, and for each of the multiples we see for 2, we see that if SP of j is equal to j, that means if that number's SP has not yet been changed, then change is to I, because we are looping from front to back, and for any smaller number, if we see the, whenever for a number we see this see a number unchanged for the first time, we set its, like we see that 2, for 4 it has not been changed, so we make it 2. For 6 it has not been changed, so we make it 2, right? So we make it 2. Make sense? Now when this comes to 3, so 3 is already set to 3, so we will loop on multiple of 3, so we come to 6, but we see that okay, it has been set to 2, so we don't change it, because 2 is the smaller one which divides 6, so we are trying to maintain the smallest prime factor, right? So that's why we don't change this particular loop over here. So that's where this condition comes in, okay. Now what about the time complexity of this particular part of the code? It would be order n log n, right? Now why is this n log n? So of course this is same loop structure that we had in Sieve of Eratosthenes, right? That okay, you loop from 2 to n, and for each of the numbers you loop on its multiple only if it's a prime. So if you only loop on multiples of prime, it's n log n. If we loop on all multiples of odd numbers, then it's n log n, right? I hope these asymptotics are clear by now. Okay, so this works in n log n. So this is a pre-computation that we are doing. So we are calculating this SP array. Now how do we use this SP array to calculate any factorization for any number? So let's suppose we are given some integer x and we want to find the prime factorization for that. So what we can do is, like, while x is greater than 0, we know that SP of x is one of the factors, so we just push it into the answer and we divide x by SP of x and then repeat this process, because it's like 60, so one of its factor is 2 and then we are left with 30, then one of its factor is 2, smallest factor is 2, and then we are left with 15, then one of its the smallest factor of 15 is 3, and then we are left with 5, the smallest factor of 5 is 5, and then we are left with 1. So as soon as we hit the 1, this while loops fail, and then we, like, this is the vector that is being created, so this is what we return, right? 2, 2, 3, 5. Okay, now what about the time complexity of this part? This will be nothing but order log n. Now we have already discussed why this is log n, because every time we are dividing it by SP of x, and SP of x is greater than equal to 2, so every time it's actually getting divided by at least 2, so this will like terminate in log n number of steps. So for every number, now you can find out prime factorization in order log n, provided you can do this pre-computation up to that number, right? So if in a problem you need to like find out prime factorization for repeated number of times for smaller range, like find out prime factorization for up to 10 to the power 6 numbers, then you can pre-compute this SP array that we talked about and repeatedly answer the factorization for any number in order log n, right? So that's all for this video. See you in the next one.